All right, I rewrote this example at the bottom of page 110 to use the equation y equals x squared instead of y equals x cubed because it'll go with this applet I'm going to show you in just a moment. So we are asked to let R be the region bounded by y equals the square root of x and y equals x squared. I'm going to stop right there and just sketch those real fast. So for y equals the square root of x, I know this is what my square root curve looks like. And then for y equals x squared, I definitely know this is what my parabola looks like. Ugh, well, that one's a little iffy actually. All right, so we are told that S is a solid whose base is R and whose cross sections are perpendicular to the y-axis are squares. Now in the applet I'm going to show you in a second, the difference is that for the applet, the cross sections perpendicular, they're going to be perpendicular to the x-axis, not the y. But really what that means is that this region bound by those two curves, that's the base of a solid. So you need to imagine that the solid is coming out off the screen or off the page towards you along what we call the z-axis. So when we graph in 3 dimensions, the third axis is called the z-axis. And instead of me doing a really terrible job of drawing this, I'm going to take you over to this Geogebra Applet and I'm going to embed it in a page in just a second. So in Geogebra, this applet's kind of limited. This is, again, the graph of x squared, and this is our square root function of x. And so what we're looking at right now is, in fact, I'm going to pick square cross sections. We're looking on this left side where my cursor is kind of roaming around. That's just a zoomed in graph. Like that is the graph that we're looking at. Over here to the right, this is like a 3D graph and we can kind of manipulate it. Oops, I can twist it. Oh no. Well, this was working fine before. Of course I start recording and now it won't work very well. We're getting all sorts of views, all sorts of angles that I didn't need. Let's see if I can refresh this. Oh, I don't know how to refresh this. Okay, I keep forgetting that I can just pause the video. So I refreshed it. And what we're looking at is the green axis that you see right there. Like that's our y-axis. The red is our x-axis. And this blue axis that's coming up, this is our z-axis. And as you can see, like this would be really hard to draw. So we're kind of seeing the flat view of the graph on the left and then the 3D graph. So as I move the square cross section around, remember it's a square. So when the two curves get further apart, the square is bigger because all of its sides are the same. And as they get close together, it gets really small. So the square that we're moving around just represents the volume, represents a cross section and it has a volume. So what we need to do is come up with some more squares. So let's look at like a couple of squares. If I spread these out, now we kind of have an idea of what the shape looks like. And just like that Riemann sum, when we increase the number of cross sections we're looking at to infinity, well, I say infinity, we're actually going to take that up to 98. It looks like when we increase the number of cross sections, now it looks like a solid. We can see that it's jagged. It's not smooth because they're a bunch of squares smushed together, but we're starting to get the idea of what the shape looks like if it were smooth. So anyways, when we go back to our graph in a second, I think it would be futile to attempt to draw this 3D image. Like it's really difficult to draw. But what I do want you to do is you're going to draw a single square. That'll be like our reference square. And so earlier when I said that on this graph that our cross sections are going to be perpendicular to the x-axis. Again, this red is the x-axis and we can see these squares are perpendicular to it. The problem is actually going to be the opposite. but again, it's kind of hard to see unless we kind of manipulate this. So I'm gonna embed this applet if you want to play around with it. I think it's pretty fun. All right, so for our cross sections, instead of using the ones that are perpendicular to the x-axis, we're gonna use the ones that are perpendicular to the y-axis. So all that means is that our squares are gonna go this way. So instead of drawing that whole image, what I would do is let's just pop out like a single square. So if I pop out a square, what I'm always gonna do is on the square, kind of like bolden the part of it that's on the base. So I can remind myself that that's on the base. And going back to what we said earlier, we said that to find the volume of a solid, we're going to integrate the area of a slice or a cross section. So our volume formula is going to be the integral of the area of the square. I'm going to write that just an A right now. And these rectangles, because they're perpendicular to the y-axis, these are going to be dy rectangles. So let's start with the easy thing first. We need to know our limits of integration. So if we're integrating with dy rectangles, then these are the lower and upper y values. So we know that those two graphs are going to intersect at 0, 0. You could probably figure out that this is going to intersect at 1, 1, but just to be sure, like if we don't remember, we could set the square root of x equal to x squared. We could square both sides to get rid of the square root. And then we would not want to divide by x here, but instead we'd want to subtract it over and factor. So we'd get like, factor out an x cubed minus 1. Then the zero product property, we would discover x is 0, which we already knew, and then we would set x cubed minus 1 equal to 0. Therefore, x cubed is 1. Take the cube root, x is 1. And I know, of course, if I plug that back in, y equals the square root of 1, I get the point 1, comma 1. So I just want to review that algebra in case something like that comes up. Don't forget to factor, don't divide by a variable. All right, so we're going to use the y values. I realize they're the same, but this is 0, the y value, and this is 1, the y value, because this is, we're using what we call dy rectangles. So basically, if they're not up and down, those are dx are up and down, side to side, are what we call dy, perpendicular to the y-axis. All right, so let's think about how to find the area of a square. I say let's think about, hopefully we don't have to think too hard. We know for a square, you could say length times width, but a square has 4 congruent sides. So we could just say the side squared. So here's where it's gonna get a little tricky. The question is, how long is the side? And it's not a number, it's not constant, just like we saw on the applet a second ago, depending like which particular square I'm looking at, some of them are bigger than others. So I can't just use a particular number. We've gotta have an equation, and it's gonna involve our functions that we're working with. So if I look at the side that I emboldened, if I look at the right side of it, well, the right side is that graph of y equals x squared. Oh my gosh, what's happening? Sorry, I have my keyboard attached to my computer right now and I leaned on it and it did something. All right, so this is y equals x squared. And then the left side is y equals the square root of x. But here's the problem, and this is why I went back to the original, like with the dy, because I kind of wanted to make this one something we've got to think about. I can't put x's in a dy integral. I can't like have x's in here. So instead of having these solved for y, I need to solve them for x. So I'm going to do that in this bottom left space. I'm trying to save the bulk of the space for the rest of this. So if y equals x squared, take the square root of both sides, the square root of y equals x. So I'm going to rewrite this as x is the square root of y. And then same with the other curve, I've got to solve that. So if y equals the square root of x, I would just square both sides to get x by itself. Y squared equals x. All right, so I need to use these two equations solved for x so that when I'm inputting, it gives me y, or involves y, I should say. All right, so if I go back to my square, this is my square cross section. It's important that we always draw the cross section. It's really important. I wouldn't attempt the 3D drawing though. So this side from right to left, it's just like what we did with the area. I'm gonna subtract the right side from the left. So the right side is the orange square root of y, or sorry, I said right side from the left. I'm gonna do right minus left. So I'm gonna subtract the left from the right. So the square root of y minus the left side, y squared. All right, so that's gonna be the side. That's the length of the side of this square. So as we move along that shape, that's gonna vary depending on what our y values are. All right, so as I come back up here, what we were thinking about over here is this area. And we said we know that for a square, our area is the side squared. So I'm gonna replace that now with this expression, the square root of y minus y squared. So that's the side. I need to square it because that is the formula for the area of a square. And then that's gonna be dy. All right, that's the hard stuff. I think putting this together in the beginning is tough. This is like my favorite topic in calculus, so it gets better, but I think it's a lot to process. So remember, this area of formula will depend on what your cross section is. It's not always going to be a square necessarily, but if we're lucky, it'll often be a square. All right, so I'm going to rewrite this. The rest of this is just stuff we can do. I'm going to maybe speed this up just so this video doesn't last for the rest of our lives. I'm going to rewrite that as y to the 1/2 minus y squared squared dy. And what I'm going to do is I'm going to I'm going to distribute that. So I'm going to just do y to the 1/2 minus y squared. I'm going to square that. And that's going to be like that formula for a perfect square trinomial. So square the first term, that's just y. The middle term is going to be 2 times the first times the last. So it's going to be 2y to the 5/2. The third term is going to be y to the 4th. And if you didn't follow that, just FOIL it out to the right. That's what we should get though. I already checked it. All right, so we're going to now integrate that. So we're just using the power rule. So when we get to this antiderivative step over here, the antiderivative of y is 1/2 y squared. Then I'm gonna have minus, I'm gonna have to add 1 and then multiply by 2/5, or sorry, no, add 1 and then multiply by 2/7. So I'm gonna get y to the 7/2, then 2 times 2/7 is 4/7. And then lastly, 1/5 y to the 5th power. Okay, and then we're gonna evaluate that from 0 to 1. So all I did just then was find the antiderivative of this function. Now when we plug the 1 and the 0 in, 1/2 times 1 squared is just 1/2. Negative 4/7 times 1 to the 7/2 power is just minus 4/7. And then plus 1/5 times 1 to the 5th power is just plus 1/5. So that's what we get when we plug the 1 in, plug the 0 in, even easier. And I'm not gonna go through it right this second, but find common denominators, etc. This should reduce to 9/70. So that is our final answer. I know that's a lot of work, but if you break it down to get one step at a time, it's important to draw this original graph and it's important to draw this cross section. But again, I don't think it's worth our time to try to draw the 3D graph.